All right, welcome back. We're going to go ahead and continue with the Honors Pre-Calculus Marking Period 3 RQA Review Number 1. We left off finishing up problem number 5, so we're going to go ahead and start with number 6. And in this video, we'll probably just do 6 and 7, and then the last video we'll finish off the review. So let's go ahead and take a look at number 6. So number 6 says, which of the following pairs of vectors are perpendicular? So the key for this is noting that two vectors are perpendicular if and only if their dot product is equal to 0. Okay, so if you look at the couple options that they give us here, some of them kind of, at first glance, may look like they give you 0. So for example, if you look at A says that you have the vector -3, 0, and 3, 0. So because you see a 0 there, it might be tempting to jump to that answer. But if you do the dot product, remember the process for that is you take the x value of the first vector times the x value of the second vector plus the y value of the first vector times the y value of the second vector. So here you would just get -9, which is obviously not equal to 0, right? So A would not be your correct answer. Okay. If you look at B says you have the vector 3, 8, and the vector -1, 3/8, right? Those are the components. So if I go through and I find the dot product of those, I have 3 times -1, right? Multiplying the corresponding x values, and then adding that to the corresponding product of the y values. So plus 8 times 3/8. Okay. So here you would get -3 from this first product, and then here the 8s would cancel, right? Because you have 8 divided by 8 plus the remaining 3, which is 0, right? So the answer would be B. The vectors 3/8 and -1, 3/8 are perpendicular to one another. Okay, so there's problem number 6. We're going to go ahead and continue with number 7 now. And this problem is pretty lengthy in the method that I'm going to solve it with. So it says Jerome and Michael, linebackers for South's varsity football team, deliver a big hit to the halfback in last weekend's game, striking the halfback simultaneously or at the same time from different directions with the following forces. Okay, so they give me that the force vector for Jerome, and I'm just going to say Fj for Jerome, is 1230 newtons. Newtons is a measurement of force, okay, at 53 degrees. And then the force vector for Michael, or Fm, is equal to 1450 newtons, okay, at 107 degrees. Okay, and they want me to determine the resultant force, in other words, the combined force applied by Jerome and Michael to the halfback. Okay, and then they have this extra piece that says the directions of the two forces are stated as counterclockwise angles of rotation with east. So in other words, if you're looking at a compass, so we'll put our compass over here. The angles in this case, and in most cases, the standard type of way to do it is being measured from east going counterclockwise, right? So you start at the east, or in other words, the positive x-axis, and you go this way, right? So for this problem, I'm going to go ahead and draw a picture first to start us out to kind of see what's going on here. Okay. Make sure you leave quite a bit of room just so you can read your notations here and understand really what's going on. Okay, so I'm going to go ahead and do Jerome's vector first, and I'm going to put him in blue. So Jerome's vector, they say, is 1230 newtons at 53 degrees, so that's somewhere in the first quadrant. Okay. Okay. And actually, let me make him red so that we can see it a little better. Okay. So the red vector, that's, we'll say fj, right? That's the vector for Jerome. Okay. And then for Michael, we'll do Michael in green. So the vector for Michael will be in green here. They say it's at 107 degrees with a force of 1450 newtons. So 107 degrees is in quadrant 2, right? Because north is directly 90 degrees. So it's somewhere like here, right? And we'll try and fit this on here. So his force was 1450 newtons, right? And they say that the angle is 107 degrees. So they're starting from here, again using the compass, starting from the positive x-axis going counterclockwise. They're starting from here and they're going over to here. That's 107 degrees. For the sake of the picture, and just because I like to measure from the x-axis, instead of saying the angle is 107 degrees, I'm going to find what this angle is from the negative x-axis, right? So if you try and find what this angle is, well, that's 180 degrees, right, over here, minus 107 degrees will give me this result here. So if you do that, you would get, what would that be, 73 degrees, right? So this angle here is 73 degrees, okay? So again, I just like to do that just because it keeps my angles separate instead of overlapping here, and we usually measure from the x-axis anyways, so I'm just going to go ahead and do that, okay? So on the next page, what I'm going to do is I need to find the x and y components for each of these forces so that I can then find the result of the two forces together. Alright, so let's go ahead and continue on the next page. So I'm going to find the component form of Jerome and his force first. So that was the this vector here, right? The red was Fj or F Jerome, so we'll keep it in red here. So let's just make a note of that. This is for Fj, right? So I'm actually going to go ahead and make a triangle out of this guy here, right? Because I need to find this x and y component and break down this vector, right? So drawing a triangle, I'll do that on the next page. We have something that looks like this, right? I'm going to make a right triangle. We know the hypotenuse, that's the total force, was 1230 for Jerome, and we know that this angle is 53 degrees, right? So I need to find y and x to find the component form of Jerome. Okay, notice that his force is in quadrant 1, so my x and y values will both be positive. Okay, that's going to be important, especially when we find the component form of Michael's force vector. So I'm going to use some trigonometry here. So if I'm looking for the value of x, well, I can do cosine of theta, or 50 degrees, is equal to x over 1230, and then I can solve for x. So we're going to say cosine of 53 degrees is equal to x over 1230. Okay, I'm going to multiply both sides by 1230 because I'm trying to solve for x. Okay, make sure you're in degree mode. Okay. And let me see what we get here. So for Jerome, we get 740.232, right? And again, we're in quadrant 1, so I can keep that positive. Okay. And then if I do the same process, we'll try and fit it in over here. You're going to do sine of 53 degrees because we're trying to find this value now. So sine of 50 degrees is equal to opposite, in other words, y over the hypotenuse, which is 1230. So y over 1230 is the exact same process. Okay, so you're going to multiply both sides by 1230. I can't fit this on the screen, but well, let me see if I can. So 1230, there we go. That'll fit, and we have y is approximately, if we do that in our calculator, 982.322, right? And again, we're in quadrant 1, so we can keep that positive. Y's are positive in quadrant 1. Okay, so there's the component form of Jerome's vector. Okay, so now I'm going to do the exact same process all over again, but now for Michael's vector, right? So Michael's vector was here in green. Notice that he's in quadrant 2, and quadrant 2 x is negative, y is positive. So when I get to this point here, whatever the x value is, I'm going to have to make negative. So let's go ahead and draw his vector just like we did on Jerome's vector here. So we're going to say this is for Michael's vector, right? So again, I'm going to set up a triangle like I did for Jerome, but I'm in quadrant 2, so it's going to obviously look a little different, also just because the angle is different. So Michael's triangle will look something like this. Right. So my goal again is to find what is this y and x component, so that just like I did with Michael's vector here, I can find the component form of fm, right? So we'll say, try and keep the same color, so we'll say fm is equal to something, comma, something, right? That's our goal. Okay. So I'm going to use the same process again as before. If I want to find the x component, I'm going to say cosine of 73 degrees, in this case, is equal to x over 1450, right? He had more of a force. I'm going to multiply by 1450 on both sides. And if we do that, we get x is 423.939. Okay. But again, remember we are in, let me go back here, quadrant 2. So x should be negative. So I need to keep that in mind and adjust that and make this a negative 429.939. Okay. And then we do the same thing over here, but with sine. So we're going to say sine of 73 degrees is equal to y over 1450. Okay, multiplied by 1450 on both sides. And if you do this, we see that y is 1,386.642. Right? And we are in quadrant 2. Y is positive in quadrant 2, so we can just go ahead and insert that here. Right? So that is the component form of Michael's vector, his force. Right? Okay. So we're about halfway there now. So now what we need to do is we need to combine Jerome's vector and Michael's vector. Okay, and to do that we simply add them. So we'll call this fj plus fm. Okay, so remember, to add vectors you just simply have to add them component-wise. So Jerome's x vector was 740.232, okay, plus Michael's vector, make sure I get this right, was 423, or excuse me, negative 423.939. Okay, so there's the x component. I'm actually going to write the y component down here just to fit it on the screen here. Okay, but the y component would be the y component of Jerome's vector, which is 982.322, plus Michael's y component, which is 1386.642. Okay, so if you add these all up, you get, let's see, if you add these up, you get 3, whoops. So, let me get my eraser here, sorry about that. So we will get 316.293. Make sure we add these right. And for the y component, the combined force is 962.703. And actually this should be much bigger. I think I accidentally made one of the y's negative. Sorry about that. So if we do this correctly, here we go. We get 2368.964. There we go. Okay. So that is the resultant vector of Jerome and Michael's force. But to actually find the overall force, this is the component form. To find the overall force, what I actually need to find is the magnitude of that. So I need to find the magnitude of Fj plus Fm, right? Well, to do that, we simply just use the magnitude formula, right? You can kind of think of your x1, y1 as 0, 0, right? You're like at the origin. So essentially I'm just squaring this x component and this y component of this new vector I just found. So if you do all that, you get 2,389.986 newtons, okay? So there's your total combined force. That was what part A was asking us really for, right? But then part B, if you look at part B, it says determine the direction in degrees that the force is being applied, right? So I need to see what is the direction that both of these vectors added together is going in, right? So what I'm going to do here is I'm going to use my Fj plus Fm, which was this vector. Notice that this is in quadrant 1, right? X and Y are both positive, so there's no addition or subtraction I'm going to have to do when I find this angle. Just whatever the answer comes out to be is going to be the answer. In other words, I don't need to do 180 minus 1 plus 180, 360 minus, right? I'm in quadrant 1. So to do this, I'm going to use tangent inverse. So I'm going to say the angle is going to be tangent inverse of the y value here. So 2368.964. 2368.964, right, divided by the other value, which was x, so we have 316.293, right? So again, make sure you're in degree mode, and if we do that in our calculator, we get 82.395 degrees, okay? Which again is in, that's a quadrant 1 angle. So that would be the total combined force. Now we have the direction of the force as well as the overall result of the force, which is here. So that answers A and B. Okay, so that is questions 6 and 7 done for you. I know number 7 is a little bit more tedious and lengthy. We'll go ahead and finish up the review in the next video. Thanks for watching.